Welcome to the presentation of the work A Blueprint for Multi-Frequency and Multi-Constellation PVT Assurance. I am Francesco Ardizzon from the University of Padua, and I will present the work done with Caparra of the European Space Agency, Fernandez-Hernandez of the European Commission, and Ardizzon. The threat of spoofing in GNSS is well known. However, the service providers are already providing several solutions. We can divide them into classes: navigation message authentication, where only the message is authenticated, typically by using cryptographic means like OSNMA, and range authentication. In the latter, the PNs are either encrypted, like for the commercial authentication service, or watermarked, as in Caparra. These solutions, however, only protect a single range signals. Thus, when completed authentication PVT, we may have issues in terms of availability or accuracy, since we are essentially using a single frequency receiver. Our goal is to complete a PVT which is both secure and accurate. We propose to do so by a series of consistency checks, starting from the subset of the signals and progressively testing the other ranges, eventually including them in the final PVT computation. In detail, first, we consider the protected signals. For instance, we can consider the ranges for the E6C band authenticated by CAS. Second, we consider the signals transmitted by the same satellites in the same band, in this case E6C and E6P. Third, signals transmitted by the same satellites but on different bandwidths. Finally, we may also include signals coming from different constellations, including, for example, GPS or Beidou. We highlight that this is just a preliminary work. We'll present a simplified version of the checks that will have to be improved in the future. Nonetheless, as you will see, results are encouraging. First, let us consider the case for signals transmitted in the same bandwidth. For instance, we may consider E6B and E6C. From the theory, we know that it is possible to model the code delay error as a Gaussian random variable, where the standard deviation is related to the correlator spacing of the tracked loop. Applying similar consideration to the pseudo range, the difference between the ranges can be modeled like in equation 1, where k is a confidence level chosen by the user. A similar check can be performed starting instead from the PLL output, where the check will be applied to the Doppler estimation. Next, we check signals transmitted by the same satellites but on different bands. In general, a pseudo range can be modeled as the sum of the range and some error contributions. Now, if we compare the two ranges, where only one is authenticated, clearly the geometric part has to be the same. The tropospheric delay difference is negligible. The ionospheric delays are related by the carrier frequencies. Thus, we can model their difference as a Gaussian random variable, where in the mean we have the interfrequency bias that can be considered deterministic, and the variance is determined by, for instance, the ionospheric delay, the two multiplet errors, and the errors induced by the processing that can be considered as statistically equal. By using the authenticated information and the authenticated messages from OSNMA, it is possible to compute the predicted pseudo range for the non-protected satellites. Hence, we model the difference of the prediction errors by picking a Gaussian model, whose variance will be a function of the inter-system clock bias and the user equivalent ranging error. This models the error residuals in its pseudo range, as shown in equation 10. Finally, we introduce the concept of security-aware protection levels. We borrow this term, used for the integrity, to give an estimation of the positioning error, according to a predetermined failure probability. To do so, we have to add to the horizontal and the vertical protection level a term which is function of the thresholds chosen for each range, that we will be including in the PVT. This models the fact that, by picking a larger threshold, we indeed include more ranges in the PVT, improving the accuracy, and so reducing the integrity part. However, we are also allowing a potential attacker an higher degree of freedom in picking the ranges that he will feed us. Thus, it's up to the receiver to find the optimal compromises between security and accuracy. We tested our procedure using real-world dataset containing signals from GPS, Galileo, B2, and GLONASS, collected while driving in a van around Rotterdam. Notice that in the first part we are in the highway, which can be considered as a rural scenario, while in the second part we are in an urban scenario. For the sake of simplicity, we assume a scenario in which Galileo, SNMA, and GAS are operative. Not having E6 measurement for our example, we will assume that all the E1 signals to be representative of the E6 measurements, or equivalently, that the E1 signals have already been successfully verified by using GAS. We focused only on the last two checks that we considered more meaningful, which were signals on different bands and signals from different systems. For all the checks, we fixed the confidence levels to key equal to 3. Thus, we can consider that our procedure is successful if you obtain a false alarm probability lower than 0.3%. First, we want to test the checks for signals transmitted by the same satellites but on different bands. In particular, we check the consistency of the range from E5 by using E1. Using the parameters from the literature and plugging them into the equations previously shown, we get 11 meters as a 3 sigma thresholds. We report the results in terms of number of failures, number of total epochs in view, standard deviation of the empirical measurements, and measured false alarm probability. All the measurements, but one, are within the expected 0.3% bound. Thus, we can consider the check as successful. Interestingly, all the failures are actually related to the urban scenario measurements. For the last check, we consider signals coming from different systems. In particular, we assume that all the Galileo ranges have been tested, and we want to perform a consistency check with the GPS measurements. As previously described, first we have to compute the prediction error for each range. Second, we compute the difference between the prediction errors, one authenticated and one not, and compare them to the threshold. That threshold is computed using the parameters from the literature. In particular, we obtain as threshold 30 meters with a 3 sigma confidence level. We reported the result for both the rule and the complete dataset scenario. In the first part, the check performs as expected. In the second, there are several failures. Notice, however, that the standard deviation is still much lower than that threshold. This is probably due to the fact that for the measurements collected in the urban scenario, the non-line of sight component is dominant. Therefore, these measurements are harder to predict. Thus, we will have to find a better model just for the urban scenario at least. We want now to empirically quantify the attacker freedom to manipulate our position. In other terms, we want to measure how far the attacker may move us while staying undetected. To do so, we run a Monte Carlo simulation where we assume that gamma was equal to 10 meters and that the attacker, somehow, knows the actual ranges measured by the receiver. Thus, it adds to the ranges a factor eta. We consider the first 20 minutes of experimental data and repeated the simulation 30 times. The figure reports the results, where the green dots are the positions computed under attack. The maximum deviation induced by the attacker was 26.5 meters, which is also the radius of the sphere. However, it is worth to notice that in the same instant, using the actual measurements, we would have had an error of 15 meters. Moreover, 43% of the times the receiver obtains an invalid PVT and rejects the measurements. Hence, This shows that our strategy will effectively limit the ability of the attacker to manipulate the position of a victim receiver. In this slide, we report the Stanford plot obtained using the vertical protection levels given output by the receiver. We consider two scenarios. In the first, we will use authenticated measurements, in this case Galileo E1, authenticated by CAS. In the second, we assume that by using check 2 and 3, we are allowed to use all the GPS and Galileo ranges. In the first case, more than 30% of the times we have a protection level higher than 100 meters. In the second, this percentage falls to the 4%. Thus, we have a great improvement both in terms of availability and performance. Still, we have to add the security part in this calculation. Being additive, the relative performance gain will be maintained. To summarize, in our work, we propose a multi-step procedure where we explore the non-authenticated signal to complete a trusted PVT solution through a series of consistency checks, retaining control of the maximum acceptable spoofing error. Still, we want to stress the fact that this is just a preliminary work, and there is still room for improvement. For example, we still have to formulate a formal expression of the security-aware protection level. And second, we have to formulate a better modeling of the statistics, especially for the urban scenario, where there have been several issues, especially with the last check.